Okay, so you're staring down the barrel of a massive exam,
Yeah.
like the GPAT 2025,
Mm-hmm.
and there's just so much information everywhere, right?
Right.
It seriously feels like trying to pick one star out of the sky, never mind figuring out how to actually, get there. How do you cut through all that static and find what really matters for exam day?
It's a classic problem, especially with technical exams like this. The potential material for the GPAT, I mean, it's huge, spans so many different sciences.
Yeah.
And without a clear path, a solid strategy, it's really easy to get lost or, bogged down focusing on stuff that's maybe not the absolute core.
Totally. A roadmap becomes essential.
Exactly. You need that structured approach.
Which is why, honestly, we were pretty excited to dive into the source material you shared with us.
Yeah.
This guide, the comprehensive guide to main topics for GPAT 2025. It doesn't just hint at a roadmap. It basically promises one.
Mm-hmm.
And for something like the GPAT pharmacy entrance exams, that kind of clear guidance, that's like gold dust.
Absolutely. So our mission today in this deep dive is really to unpack that guide. We're going to walk through it, look at how it breaks things down section by section.
Yeah, pull out that roadmap.
Pull out the roadmap it offers, highlight the key areas it stresses, the specific concepts it flags as important. We want to give you a structured look based just on what's in this source and what it suggests is important for your GPAT 2025 prep.
So yeah, think of this like we're sitting down with you, we've got the guide spread out, and we're figuring out the best way through this challenge together. Because tackling a national exam for pharmacists, that crucial step for MPharm admission, it feels like climbing a mountain.
It really does.
But having a guide like this, a GPAT pharmacy syllabus broken down, it just makes it feel, well, maybe less intimidating. Like you have a starting point, you have waypoints, a clear path.
It frames the challenge differently. And the graduate pharmacy aptitude test, the GPAT exam, is that critical gateway for MPharm admission in India. Success really does hang on having a good strategic study plan. And this source says it provides exactly that, this detailed roadmap. What's interesting right from the start is how it tries to organize the sheer vastness of pharmacy science, the stuff tested by the GPAT exam pattern, into these main topics.
Okay, so let's unpack that roadmap. How does it start? What's the overall strategy it suggests?
Well, it kicks off immediately by hammering home the need for a strategic approach. It's not just study lots.
No.
It specifically says you need to cover a broad spectrum of topics strategically if you want to excel in the exam.
So that strategic bit isn't just about hours logged, is it? It's about, direction and focus.
Precisely. It's about studying smart. And for a wide-ranging exam like GPAT, covering everything from basic chemistry to applied pharmacy, strategic means understanding how these subjects connect, maybe knowing their relative weight, though this guide doesn't specify weightings, and really allocating your time effectively.
Okay.
And this source immediately lays out that broad spectrum. It gives us the main pillars of the GPAT 2025 syllabus right up front. Physical chemistry, inorganic chemistry, organic chemistry, pharmaceutical chemistry, pharmacology and medicinal chemistry, biochemistry and microbiology, and legal and regulatory affairs. 7 main areas.
Wow. Okay.
And the whole guide, its roadmap, is built around these 7 pillars.
So right away, it gives us the big picture,
Yep.
the main territories you need to conquer for the GPAT exam. It's basically the GPAT syllabus broken down, sets the stage.
Exactly.
All right, let's dive into the specifics then. One by one, according to this guide you shared. Where does it start us off?
It starts right at the foundation, the most basic science underpinning everything else, physical chemistry.
Okay.
The guide calls it the backbone for understanding chemical phenomena, says it's crucial for problem-solving skills and conceptual clarity.
That makes sense. Like you need the fundamental rules of how stuff works before you can understand drugs, right?
Exactly. How drugs behave, how they interact, how we formulate them. It all comes back to the basic physics and chemistry of the molecules involved. You need the rules of the game first. And what's interesting is how this source breaks down physical chemistry. It starts with the absolute basics. Basic concepts.
Like what?
Units and measurements, SI units, the mole concept, molarity, normality. Seems simple, maybe.
Yeah, kind of fundamental.
But why emphasize these for GPAT? Because they're the language you need to quantify anything in pharmacy. Preparing an IV solution. You need precise units, you need the mole concept for weights, molarity or normality for concentrations. Get these wrong.
And everything else is off.
Exactly.
Right.
Non-negotiable building blocks.
Okay, what else in physical chemistry?
Then it lists the gaseous state. Ideal gas law, real gases, van der Waals equation.
Gases. My first thought is, why gases specifically for pharmacy? Most drugs aren't gases.
That's a fair question, but think about medicinal gases, oxygen, nitrous oxide used in anesthesia. Their behavior follows these laws.
Oh, okay. Good point.
Plus, understanding gases helps understand pressure and temperature effects in processes like, say, freeze-drying lyophilization or sterilization with steam, and the difference between ideal gases, which is a simplification, and real gases using van der Waals. That's important because real-world conditions, like in the body or in manufacturing, aren't always ideal. The GPAT exam pattern could definitely test this foundation, maybe in an applied way.
Got it. And solutions. That seems way more obviously pharmacy related.
Oh, absolutely. The source highlights this strongly. It mentions colligative properties, vapor pressure, boiling point elevation, freezing point depression, osmotic pressure.
Right.
Understanding solutions is just vital for making any liquid dosage form syrups, injections, little drops. And a key insight for GPAT prep. Osmotic pressure is critical for IV solutions. They need to be isotonic with blood, same osmotic pressure, or you damage blood
Oh,
cells.
that's crucial.
So calculations using molarity, molality, these properties, very common GPAT questions because they're fundamental to safe medicine formulation. Direct application.
Okay. What about chemical equilibrium? Le Chatelier's principle, equilibrium constants. How does that play in?
This is about reactions that can go both ways, finding a balance. In pharmacy, it helps predict reaction outcomes in synthesis or storage, but maybe more importantly, it explains how drugs exist in different forms.
Like ionized or unionized?
Exactly. Depending on the pH stomach, blood, wherever an acidic or basic drug shits between forms. And this equilibrium massively impacts how well it dissolves, how it crosses membranes for absorption, how it gets around the body. Le Chatelier helps predict those shifts. The GPAT pharmacy syllabus definitely expects you to link this chemistry to drug behavior.
Interesting. Then there's thermodynamics. Laws of thermodynamics. Enthalpy, entropy, Gibbs free energy. It feels a bit like pure physics.
It has deep roots in physics, sure, but it's absolutely critical for pharmacy. Thermo deals with energy and, crucially, whether a process will happen spontaneously. First law is energy conservation. Second law brings in entropy, disorder. And Gibbs free energy, that's key. A negative Gibbs means a process is spontaneous under constant temperature and pressure.
Why is that important for drugs?
Well, it predicts if a synthesis reaction will work, if a drug might precipitate out of solution, even how strongly a drug binds to its target. It also helps predict and control drug stability, how temperature affects degradation rates. Basic thermo principles definitely show up on the GPAT exam pattern.
All right. Electrochemistry is next. Cells, Nernst equation, corrosion, batteries. Again, how does this connect to medicine?
Yeah, it might seem a bit distant, but electrochemical reactions can degrade drugs. Some lab tests for quality control use electrochemical methods. The Nernst equation relates to ion behavior, may be relevant for biological systems or sensors. And corrosion. Think about drug packaging, like metal tubes or components of devices. Are they compatible? Will they corrode and contaminate the product? So it has its specific applications within pharmacy, relevant for the GPAT pharmacy entrance exam.
Okay, makes sense. Atomic structure is also in this section. Quantum mechanics, Bohr model, orbitals, periodic trends. Back to the absolute basics.
Right down to the building blocks. And understanding these is essential for both inorganic and organic chemistry, which are huge for pharmacy, how electrons behave, the shapes of atomic orbitals that determines how atoms bond to make molecules.
Covalent bonds.
Ionic bonds.
Exactly. And periodic trends, how size, ionization energy, electronegativity change across the table. Super useful for predicting how elements will behave, how strong bonds will be, what reactions they'll undergo.
And predicting behavior is useful because
Because a drug's properties, solubility, reactivity, how it interacts with your body, all stem from the atomic properties of its elements. Knowing trends lets you make educated guesses without memorizing every single detail. This foundational stuff is definitely tested on the GPAT exam pattern, often related to structure and bonding.
last one in physical chemistry, surface chemistry. Adsorption, catalysis, colloids, emulsions. This deals with what happens at interfaces where different phases meet. Adsorption, things sticking to surfaces, is relevant for chromatography, which we use for analysis, and maybe drug binding. Catalysis, speeding up reactions, is huge in drug synthesis.
And colloids and emulsions, they sound very pharmacy-like.
They really are. Colloids are dispersions, like tiny particles spread through a liquid. Emulsions are one liquid dispersed in another, like oil in water. What's the key insight for GPAT prep here? Many drug delivery systems are colloids or emulsions.
Like IV fats or creams and lotions.
Exactly. 5E lipid emulsions, micellar carriers, topical creams, lotions, even some oral liquids. Understanding how to make them, keep them stable, their properties like particle size. That's crucial for effective drug delivery. This area directly links physical chemistry to practical pharmaceutics, definitely a high-yield GPAT topic. So, just to loop back, how does mastering all this physics-based chemistry actually help someone aiming for the GPAT pharmacy entrance exam?
Well, it's clearly not just theory for theory's sake. It's the why behind everything else. Why a drug dissolves like it does, how it gets across membranes, how stable it is, how manufacturing processes work physically. Without this foundation, all the other pharmacy stuff would just be facts to memorize. It wouldn't give you the deep understanding you need to solve problems. It's the scientific lens, really.
Perfectly put. It provides that essential lens. And from those fundamental physical rules, the guide then logically moves to the elements themselves in inorganic chemistry.
Right. This part, according to the source, looks at metals, nonmetals, the periodic table again, coordination chemistry, and some practical stuff relevant to the GPAT pharmacy syllabus.
Exactly. It starts logically with the periodic table, organization, properties, trends, predicting behavior.
So building right on the atomic structure stuff. The periodic table is the master map.
Precisely. And knowing the trend size, electronegativity helps predict bonding and reactivity. Why is this useful? Well, while most drugs are organic, some do contain metals like lithium or iron supplements.
Or things used in imaging, right?
Yeah.
Like MRI contrast agents.
Good example, gadolinium complexes. And some cancer drugs are metal-based, like cisplatin. So understanding the basic chemistry of these inorganic elements, their typical behavior, helps understand these specific types of drugs or agents.
The guide specifically flags coordination compounds, naming bonding theories like valence bond theory, crystal field theory, isomerism. That sounds pretty specialized.
It's focused on metal chemistry. Coordination compounds have a central metal atom bonded to surrounding groups called ligands. Key takeaway for GPAT. Many vital biological molecules are coordination complexes, think hemoglobin with iron-binding oxygen. And some drugs are too. Knowing how to name them is important. Understanding the bonding theories, even basically, helps explain why they have certain colors or magnetic properties which can relate to their function. And isomerism, different arrangements of ligands, can lead to different biological effects, just like with organic drug stereoisomers. GPAT questions might test naming, structure, or maybe basic bonding concepts related to these compounds.
Metallurgy is also listed. Extraction, refining, applications like alloys or metal-based drugs. Seems a bit industrial.
It leans that way, yes. But its inclusion suggests relevance to understanding the source and purity of materials. A pharmacist isn't doing the extraction, but knowing how metals are obtained and purified gives context to potential inorganic impurities in pharmaceutical ingredients.
So it links to quality control.
Exactly. And the applications mentioned, alloys in instruments, metal-based drugs, show direct pharmaceutical relevance. It's about the material science aspect.
And the last bit, in inorganic, qualitative analysis, detecting ions, confirmatory tests, and its relevance for drug impurity analysis.
This is classic lab chemistry, identifying what's present using simple tests like precipitation or color changes. Why is it important for GPAT? Because these basic techniques are fundamental tools for quality control.
Checking raw materials or final products for unwanted stuff.
Precisely. Checking for inorganic impurities that shouldn't be there, ensuring the drug is pure and safe. It directly links basic inorganic reactions to essential pharmaceutical quality assurance, a likely area for practical application questions on the GPAT. So, connecting inorganic chemistry to the bigger GPAT syllabus picture, it gives you the tools for understanding the elements beyond carbon that play roles in pharmacy, whether as drugs, manufacturing aids, or impurities. It complements the organic side.
By broadening the view. Okay, so from elements and metals, the guide moves into what feels like the heartland. Organic chemistry. The source calls this fundamental for understanding drug synthesis, mechanisms, and functional group transformations.
This has got to be core for pharmacy, right? Since most drugs are organic molecules.
Oh, absolutely. Organic chemistry is arguably the most central chemical discipline for pharmacy. Understanding how these carbon-based molecules are built, how they react, how structure relates to function. It's foundational for everything that follows, like medicinal chemistry and pharmacology. The guide wisely starts with basic principles, like reaction mechanisms, nucleophilic substitution, elimination. Why is knowing the how of reactions, the step-by-step process, so critical?
That's a great question. Understanding mechanisms is key because making drugs is all about reactions. Knowing the mechanism helps predict outcomes, spot potential side products or impurities, and design better ways to make the drug.
And it helps understand how drugs react in the body, too.
Definitely. Like during metabolism by enzymes or reactive intermediates form, the GPAT exam pattern often tests common organic mechanisms in their applications, sometimes in a drug context.
Okay. And stereochemistry is back again. Chirality, optical activity, and enantiomers. It must be super important if it keeps popping up.
It absolutely is, and seeing it here again stresses its huge importance in pharmacy. Remember, biological targets, receptors, enzymes are chiral themselves, like hands.
Left and right hands.
Exactly. So they interact differently with the two mirror image forms, the enantiomers of a chiral drug. One might work perfectly, the other might do nothing, or worse, be harmful.
Like the thalidomide example.
The classic, tragic example. So understanding stereochemistry is vital for drugs' specificity, safety, efficacy. The GPAT pharmacy syllabus tests this heavily RS configuration, optical activity, different effects of enantiomers.
The guide also mentions protection and deprotection strategies in synthesis. Sounds complicated.
It's a technique used when you're building complex molecules, which many drugs are. If you want to react one part of the molecule but not others, you temporarily protect the other reactive bits.
Like putting masking tape on something before you paint.
That's a decent analogy, yeah. Then you do your reaction, and then you deprotect, take the tape off. It's about controlling complex reactions to get the specific drug molecule you need.
Okay. Then the guide lists the basic carbon structures. Hydrocarbons, alkanes, alkynes.
These are the simplest skeleton single, double, triple carbon bonds. Foundational stuff. You build everything else on top of these. It also lists aromatic compounds, especially benzene chemistry, electrophilic substitution. Aromatic rings seem to be everywhere in drugs. They are incredibly common. Aspirin, paracetamol, diazepam, loads of them. Why? Aromaticity gives special stability and electronic properties that really influence how the molecule behaves its solubility, how it interacts with targets, and electrophilic aromatic substitution. That's a key reaction for attaching other groups onto these rings, a common step in making or metabolizing drugs. The GPAT exam pattern tests aromaticity and these key reactions because they're so central to drug structures.
Moving on to functional groups. Alcohols, phenols, ethers, prep reactions and relevance like antiseptics, solvents.
Right. Functional groups are the reactive parts of molecules. Alcohols, phenols, ethers are fundamental. Knowing their basic chemistry is essential. And their relevance is direct. Ethanol is an antiseptic. Phenol derivatives are disinfectants. Ethers were early anesthetics. Plus, they're building blocks for many other drugs.
Aldehydes and ketones next. Reactions like nucleophilic addition use as intermediates.
These have the CO group, the carbonyl. Their key reaction is adding nucleophiles. They're very common intermediates used to build more complex drug structures. Understanding their reactivity is key for planning how to make drugs, something the GPAT might test related to synthesis pathways.
Carboxylic acids and derivatives like esters and amides. The guide links them to NSAIDs and antibiotics.
Another hugely important group, the NES-EOH group and its relatives. So many drugs have these. You mentioned NSAIDs like ibuprofen, they have the acid group. Beta-lactam antibiotics like penicillin, they have amide bonds. Understanding their acidity, how they react, is vital for understanding how these drugs are made, how they behave in the body, like ionization affecting absorption, and how they might break down. Definitely a high-yield area for GPAT.
And the last one in organic, amines and biomolecules. Amines, basicity synthesis, and biomolecules like carbohydrates, amino acids, proteins.
Amines contain nitrogen, also super common in drugs. Think adrenaline, antihistamines. Their basicity is really important because it affects ionization at body pH, which impacts everything from solubility to target binding. And listing biomolecules here, that's key.
Why list them under organic?
Because fundamentally, carbohydrates, amino acids, proteins are organic molecules, and understanding their basic structure is essential because proteins are often the targets for drugs. Receptors, enzymes, amino acids build those targets. Carbohydrates are involved in energy and cell function. This explicitly bridges organic chemistry structure to biological function, leading straight into biochemistry and pharmacology. So yeah, organic chemistry is where you really see the molecular complexity of drugs taking shape. And it forces that critical question the GPAT will ask you in various ways. How do all these structural details, the atoms, the functional groups, the 3D shape, actually translate into the drug's effect, its journey in the body, its safety?
That question feels like the perfect setup for the next section. The guide calls it pharmaceutical chemistry, saying it bridges chemistry with pharmacology, focusing on drug structures and their biological activities. This sounds like where the molecule truly becomes the medicine.
Exactly. This is the discipline zeroing in on the drug molecule itself, its chemistry, structure, synthesis, stability, and crucially, how that structure relates directly to its biological effect. It builds right on top of the organic and inorganic chemistry foundations.
It starts with drugs and their classifications, types like analgesics, antibacterials, and sources, natural versus synthetic.
This just sets the stage, organizing the drug world. Knowing the major classes, what they treat, and where drugs come from, plants, microbes, labs, is basic knowledge, often tested straightforwardly on the GPAT pharmacy entrance exam.
Then, a big one, structure-activity relationship, SSR. How changing the molecule affects activity used for designing better drugs. This sounds critical.
It is critical, fundamental to medicinal chemistry, and a very high-yield topic for GPAT. Think of the drug as a key, and the biological target, like a receptor, as the lock.
Okay.
SAR is studying exactly which features of the key, its shape, its chemical groups are needed to fit and turn the lock to cause an effect. Small changes to the key.
Can make a huge difference.
Huge! It can change how well it binds, how strong the effect is, whether it activates or blocks the target, or even cause side effects.
So SAR isn't just observing, it's a tool for design.
Precisely. It's used to rationally design better, safer drugs. By figuring out which parts are essential for activity, that's the pharmacophore, we'll get to that, and which changes improve things like solubility or reduce toxicity, chemists can tailor molecules. GPAT questions often ask how a specific structural change might impact a drug's properties, directly testing SAR understanding.
And guess what's back? Stereochemistry, chirality, and enantiomers having different effects, importance for safety and efficacy. Third time.
Yes, and putting it here emphasizes the pharmaceutical consequences of this chemical property. Because biology is chiral, the two mirror image enantiomers of a drug can act completely differently. One might be the medicine, the other inactive or toxic.
So sometimes they sell just one form.
Right. Sometimes you get the mix, racemic, like ibuprofen. Other times, just the active one, like esomeprazole. Understanding this is vital for dosage, safety, efficacy. GPAT loves questions on identifying chiral centers or comparing enantiomer effects.
The guide also folds in pharmacology basics here. Mechanisms of action, receptor binding, enzyme inhibition, and pharmacokinetics. ADME absorption, distribution, metabolism, excretion.
Yeah, while pharmacology is its own big section later, including the basics here highlights how inseparable the chemistry is from the biology. Mechanism of action is how the drug works molecularly, binding a receptor, blocking an enzyme.
And pharmacokinetics, ADME, that's what the body does to the drug, right?
Exactly. Absorption, getting in, distribution, going around, metabolism, breaking down, usually in the liver, excretion, getting out, usually urine or feces. Understanding ADME is essential for figuring out dose, frequency, and how patient factors might change things.
And the chemistry connects how?
The drug's chemical properties, solubility, lipophilicity, fat liking, ionization drastically influence every ADME step. How well it crosses membranes, where it goes, how it's metabolized. GPAT questions love to link structure changes to ADME outcomes. What's really cool here is seeing that direct line. A small chemical change, organic chemistry SAR, has this massive ripple effect on how the drug works, mechanism, and how the body handles it, ADME. That connection is key for a pharmacist.
Okay, so from the molecule acting in the body, the guide shifts focus to how we actually prepare and deliver that molecule.
Yeah.
That's pharmaceutics, which the source calls vital for pharmacy practice, covering drug delivery systems, formulation stability.
Right. Pharmaceutics is a science of dosage forms. You can have the world's best drug molecule, but if you can't get it into a stable, effective, patient-friendly form, it's useless. This is where a lot of the physical chemistry principles get applied.
It starts with dosage form design. This forms like tablets, capsules, injections, suspensions, and considerations: bioavailability, stability, patient compliance.
This is about choosing the best delivery method. Tablets, capsules for oral, injections for bypassing the gut, suspensions for poorly soluble drugs. The considerations are crucial for GPAT. Bioavailability, how much drug actually reaches the bloodstream, is key.
Affected by how it dissolves, first-pass metabolism.
Exactly. Stability ensures the drug stays good over its shelf life, avoiding chemical breakdown due to heat, light, moisture. Patient compliance is about making it easy to take correctly. GPAT questions often link formulation choices to bioavailability or stability problems.
Then pharmaceutical techniques, manufacturing methods like granulation, compression, sterilization, and quality control like uniformity, disintegration, dissolution.
These are the hands-on processes. Granulation helps powders flow for tableting, compression makes the tablet, sterilization kills bugs for injections, and quality control, essential checks before release.
Uniformity, making sure each pill has the right amount.
Yes. Disintegration, how fast it breaks apart. Dissolution, how fast the drug dissolves out. Dissolution is super important as it often predicts how well the drug will be absorbed in the body. These practical methods and tests are very relevant for GPAT questions on manufacturing and quality.
Formulation and manufacturing processes mentions excipients and process optimization. What are excipients again?
They're the inactive ingredients, but they're absolutely critical. Fillers, binders, disintegrants, lubricants, colors,
The
flavors.
stuff besides the actual drug.
Right. They're crucial for making the product flow compression, keeping it stable, controlling drug release, immediate versus slow, and making it acceptable to patients. Understanding their roles is important. Process optimization is just about fine-tuning manufacturing to get consistent, high-quality results every time.
And the last bit in pharmaceutics, stability studies. Conditions like temperature, humidity, light, purpose. Determining shelf life and packaging.
This is how we know how long a drug is good for. You test it under different conditions, often accelerated, hotter, more humid, to predict long-term stability.
That's where expiration dates come from.
Exactly. And it tells you how to package it, maybe amber bottles for light protection or special packaging for moisture. Understanding stability testing and factors affecting degradation connects chemistry, kinetics, to practical drug storage, very relevant for GPAT. So this raises that connecting question again. How do all those physical and chemical principles, solubility, kinetics, particle size, functional groups, actually get used to design, make, and test a safe, effective dosage form?
It's where the science hits the road, isn't it? Applying all that fundamental knowledge to create something tangible that helps patients, turning the molecule into the medicine.
Perfectly said. Okay, so we've got the molecule, the formulation. Now let's look deeper at how drugs affect the whole biological system and how new ones get discovered. The source links pharmacology and medicinal chemistry here, exploring drug effects on biological systems, design, and development. This goes beyond the basics we touched on earlier.
Yeah, digging into the how of drug interactions with living systems more broadly.
Yeah.
And the whole process of inventing new therapies. This feels like the real integration point.
It starts with principles of pharmacology, listing drug receptor interactions, agonists, antagonists, and the dose-response relationship. Efficacy, potency. Let's nail these down, they're fundamental. Receptors are usually proteins that drugs bind to. An agonist binds and activates it like a key turning the lock.
Mimics the body's own signal.
Often, yes. An antagonist binds but doesn't activate. It just blocks the lock, prevents the real key or other agonists from working. And the dose-response relationship. That's about how effect changes with dose.
Efficacy and potency.
Efficacy is the maximum effect a drug can produce. How much can it ultimately do? Potency is how much drug you need to get a certain effect. A drug can be very potent, need tiny dose, but have low efficacy, small max effect, or vice versa. GPAT questions love testing these terms, sometimes with graphs.
Okay. Then the guide uses examples. Autonomic nervous system drugs, CNS drugs like sedatives, stimulants, and drugs affecting the sympathetic and parasympathetic systems.
The autonomic nervous system, ANS, runs involuntary stuff, heart rate, digestion. Sympathetic is fight or flight, parasympathetic is rest and digest. Drugs targeting the ANS mess with these systems, affecting neurotransmitters like adrenaline or acetylcholine.
Used for blood pressure, asthma,
Yeah.
lots of things.
Huge range. CNS drugs affect the brain, mood, alertness, sleep. Understanding the basics of these systems and the main drug classes that target them is core knowledge because these drugs are so widely used. A big, high-yield area for the GPAT pharmacy syllabus.
Cardiovascular drugs are another major group. Antihypertensives like beta blockers, ACE inhibitors, diuretics too.
Drugs for the heart and blood vessels. Again, massive area, high blood pressure, heart failure. Beta blockers slow the heart. ACE inhibitors relax blood vessels. Diuretics make you pee out excess salt and water, lowering blood volume and pressure. Knowing the main classes and how they work is critical for GPAT.
Antibiotics and antifungals, mechanisms, and importantly, resistance issues.
Anti-infectives. They usually target something essential in the microbe that's different in human cells, like the cell wall. But resistance, that's the huge challenge.
Also bugs.
Exactly. Microbes evolving so drugs don't work anymore. This makes infections deadly again. It highlights the need for new drugs.